Dear learners, greetings to all. I am Franklin Phillips, Assistant Professor, Department of Chemistry, Bishopur College, Trichinopalli. So today we are going to discuss about some basic concepts in molecular spectroscopy, especially what is electromagnetic radiation, and then the second topic is the Einstein probability theory. So what is the purpose of molecular spectroscopy? So it is a keen interest of every researcher. Suppose any researcher, suppose they prepared a molecule, the keen interest of that particular researcher is what is the structure of my compound, my molecule. So this is a keen interest of every researcher. So there is no direct technique to find out the structure of that particular molecule what they found. But there are a lot of indirect techniques that is called spectroscopy. So through these indirect techniques, the scientists or researchers, they predict what may be the structure of my molecule. So this is the basic intention of every researcher. Okay, so with this basic idea or some preface, we just enter into this topic, molecular spectroscopy. Okay, so as already mentioned, so the scientists are deeply interested in knowing the structure of molecule, but there is no proper techniques to find out directly the structure of those prepared molecules or systems. Okay. So as per this molecular spectroscopy deals with the transition that molecule undergoes between the energy levels. Okay, when you are pausing the radiations, what happened when the molecule in the ground state, what happened in that particular system. Okay, so the molecule undergoes between its energy levels on absorption of radiation of suitable frequency. So this particular word is very, very important. The radiation of suitable frequency. Okay, so just consider two energy level. I can say En, this is the lowest energy level, and Em is somewhat higher energy level. Consider two molecular energy levels, En and Em. Okay, suppose when you are pausing a radiation, just consider the molecules in the ground state. Okay, you are pausing the radiation. Okay, after gaining energy from the radiation, it goes to the higher excited level. Okay, so what is the condition here when you are what is the condition to promote a system or a molecule from the ground state to excited state? If a photon of frequency nu falls on a molecular system, just consider in the ground state, and its energy h nu is exactly matches with this energy difference. So this is the main condition. Okay, so suppose if you want to promote a molecule or system from the ground state to excited state, it should satisfy some condition that is called the energy difference, the h nu. The energy h nu is exactly matches with the delta energy difference between these energy levels. Okay, so then the molecules undergoes a transition from the ground state to the excited state. It is called after gaining energy from the photon, and it goes to the higher energy level. So the spectrum obtained in this condition, it is called absorption spectrum. Then second thing, if the molecule falls from the excited state to the ground state with the emission of photon of same frequency, this is another condition. If the molecule falls from the excited state to the ground state with the emission of photon of energy h nu, then the spectrum obtained is called emission spectrum. Clear? What is absorption spectrum? What is emission spectrum? There is a subtle difference between the absorption spectrum and the emission spectrum. Okay, now come to another basic concept, the electromagnetic spectrum. Just tell me why it is called electromagnetic spectrum. How they named the electromagnetic spectrum? So the name itself explained, it is self-explanatory one. The electromagnetic spectrum, name itself explained, it is electromagnetic. So it consists of both electric field as well as the magnetic field. So the electromagnetic theory suggests that an alternating current in the circuit, just imagine the particle moves in a circle, okay. So suggests that the alternating current in a circuit radiates energy in the form of waves, okay. It radiates energy in the form of waves having both oscillating electric and magnetic field, and they are perpendicular to each other, okay. So once again I repeat, I tell you, this theory suggests that alternating current in a circuit which radiates energy in the form of waves having oscillating both electric and magnetic field, and they are perpendicular to each other to the direction of propagation, okay. So this simple diagram explains what is electromagnetic radiation, okay. So that's why, so as the radiation possesses both electric and magnetic field, that's why the name is called electromagnetic radiation, okay. So they travel with a velocity of light and can be treated in terms of frequency of oscillating electric as well as the magnetic field. So now we are going to relate all these factors, frequency, wavelength and velocity, with the help of this equation C, which is equal to nu lambda, and the energy associated with that particular wave. The energy associated with that particular wave, it is E is equal to h nu. You know very well, nu is C by lambda. So E is equal to h into C by lambda. Okay. Now come to another important topic, the regions of the spectrum. So now we understood what is electromagnetic spectrum. Electromagnetic spectrum, it comprises of lot of spectroscopic fields. So now we come to the another topic, the regions of spectrum, okay. So the regions of radio frequency to gamma rays. So this is called the electromagnetic spectrum. So together is called the electromagnetic spectrum, okay. So the different regions are based on the experimental techniques used in generation and detection, okay. So the name, the visible region, is based on detection of the system. So we can see through our naked eye, so what is happening, okay. So the name visible region is based on the detection of system. It occupies only a very small region in the electromagnetic spectrum, okay. So one of the units actually be used in this spectroscopy. So these are the basic units. The commonly used units for wavelength is meter, centimeter, micrometer, nanometer, and and angstrom, okay. Most probably in molecular spectroscopy we represent only in wave number. So that's why we change the previous equation. So in molecular spectroscopy, very often instead of frequency we use wave number. So nu bar, which is equal to nu by C, it is nothing but 1 by lambda. So it is usually expressed in centimeter inverse or meter inverse, okay. Now come to the regions. So what are the regions? So here we arranged in the increasing order of their frequency, okay. In increasing order of their frequency we arrange the electromagnetic spectrum, okay. Now we start from radio frequency region. See here, the frequency is 3 into 10 power minus 10 power 6 to 10 power 10 hertz. But look at the wavelength, it is 10 meter to 1 centimeter, 1 centimeter, okay. So in this way the frequency is increased, but wavelength is decreased. So when you apply the previous slide equations, you may got this result, okay. So the radio frequency region, so the nuclear magnetic resonance spectroscopy comes under radio frequency region. And come to microwave region. So here we are going to study the rotational spectrum of the system. And next, infrared spectroscopy, we are going to talk about the vibrational spectroscopy. And the next one is the visible and ultraviolet region. So here we are going to study the electronic spectroscopy of the molecule, okay. Then next one is X-ray region, and another one is gamma region. And you should remember what is happening here. So we are arranging this electromagnetic spectrum in the increasing order of their frequency, and look at this wavelength, it is decreased from top to bottom. And one other type of spectroscopy is the Raman. So it gives the information similar to microwave as well as the infrared region. Okay, another one. Come to the topic. It is very important topic. It is a basic one. The Einstein transition probabilities. Einstein transition probabilities. Okay. So here we are going to talk about three kind of what is that? Systems. Okay. The Einstein considered a system of molecules and the radiation in equilibrium. Okay. So he considered three kinds of transition. So he considered three kinds of transitions of molecules between two energy levels. I considered E1 and E2. Okay. So first transition I can name it as induced absorption. What is induced absorption? You know, induction. Induce means you have to give energy to promote a system or molecule from the lower energy level to higher energy level. Okay, so name itself, it is a self-explanatory one. So the induced means you should give some energy to promote a molecule or system from the lower energy to higher energy level. So the same is happening here. So what happened? So here just consider the molecule in the ground state. Okay, so before absorption, see here in the molecule or system, I can say the system. The system, it is in the lower energy level E1. Okay, so the molecule in the level E1 or rise to E2 level, somewhat higher energy level, due to absorption of photon of energy. Okay, so after passing radiation, the system gains energy from the radiation, and it promotes to the higher energy level E2. So the energy difference delta E, E2 minus E1 is nothing but H nu 12. What is nu 12? So you are promoting a system from energy level 1 to energy level 2. So in order to symbolize the transition, you can call it as H nu 12. Okay. So this process is called induced absorption. So now you understand what is induced absorption, what is the energy equation for induced absorption. Okay. Now come to second one. Okay. Then Einstein postulated that. So the rate of induced absorption. So he calculated the rate of induced absorption dN12. So what is dN12? The transition from lower energy level to higher energy level 2. Okay. So dN12 by dt is directly proportional to number of molecules and number of systems in the lower energy level or lowest level, ground state level. And the second thing, density of radiation you passed. Density of radiation you pass in terms of frequency. So it is nu 12. So therefore the rate of induced absorption dN12 by dt is nothing but B12 N1 into nu 12. So B12 is nothing but Einstein coefficient for induced absorption. N1 is number of molecules or system in the ground state, and nu 12 is a frequency of radiation you passed. Next come to spontaneous emission. It's quite natural. What happens? So now you excited a molecule. It is in the excited state E2. Just imagine. Okay. So if the molecule in the excited state E2, it can fall down to the ground state E1 with the emission of energy H nu 21. See the difference? So now after promoted to the excited level, the second process, spontaneous emission. In spontaneous emission, the molecules in the excited state, it fall down to the ground state after the emission of E is equal to H nu. Here I mentioned nu 21. What is nu 21? So the molecule or the system fall down from the excited state, say for example E2 to E1 level. So that's why I mentioned H nu 21. So this particular process is called as spontaneous emission. Again, Einstein postulated this process. It is called the spontaneous emission. it is the rate of spontaneous emission dN21 by dt is directly proportional to number of molecules in the E2 level. Number of molecules in the E2 level. Therefore, the rate of spontaneous emission is nothing but A21 into N2. Okay. So, since it is a spontaneous emission, so there is no need of keeping the frequency. So, that is why, so I am keeping A21 the constant and N2 number of molecules in the excited state. So, A21 is nothing but the Einstein coefficient for the spontaneous emission. Now, third one is, it is a very important one, it is a stimulated emission. What is stimulated emission? We have give additional energy to fall down, to come down to the ground state. Okay. See here, already you excited a molecule or system, it is in the excited state. Okay. So, after Einstein suggested that under certain condition, what happened here? A molecule in the excited state, under the influence or under the impact of the photon of frequency nu21. Why nu21 frequency? You should transfer the system from the excited state E2 to E1. Okay. So, under the influence of photon of frequency nu21 incident on the system, the molecule is induced to emit a photon of the same frequency. Okay. So, these two photons, they are in same phase and they have the photon has higher energy. So, the two photons are in same phase and an enhanced coherent radiation results. So, now the intensity of radiation is very, very high. So, when you compare spontaneous emission and this induced emission, so the intensity of radiation emitted from both spontaneous or stimulated emission, when you compare, the intensity of radiation comes from because of stimulated emission is very higher than the spontaneous emissions. Again, Einstein postulated that here the rate of stimulated emission is nothing but the number of molecules N2 in the excited state, and here you can include the frequency because you are additionally giving the energy. So, the density of radiation nu21 which is incident on the molecule in the excited state E2 level. Okay. So, therefore, the rate of stimulated emission dN21 by dt is nothing but B21 N2 and also include the frequency of the radiation you pass nu21. So, you know very well B21 is Einstein coefficient for the stimulated emission. Okay. Now, under equilibrium condition, so rate of absorption is equal to the net rate of the emission. Now, you are equating the previous slide equations. Okay, the rate of absorption is equal to the rate of the emission. So, therefore, B12 N1 nu12. So, this equation for rate of absorption, and this is for stimulated emission and spontaneous emission. Okay. So, A21 N2 it is spontaneous emission and this is for stimulated emission A21 N2 plus B21 N2 nu21. Okay. So, after rearranging this equation, finally you have N2 by N1 B12 nu12 divided by A21 plus B21 nu21. You know what is the difference between 1, 2 and 2, 1. Okay. So, at equilibrium, the number of molecules in the ground state and the excited state, namely N1, N2, okay, so satisfy the Boltzmann distribution law. Okay, when you talk about equilibrium condition, okay, so it should satisfy the distribution law. So, what is Maxwell distribution law? So, distribution is expressed, it is nothing but Pi is directly proportional to e power minus ei by kt. So, you know very well e power minus delta e by kt, you know this equation. So, Pi is the proportionality of the system being in that particular level, particular state I, and Ei is the energy of that particular state or level, and kt is the constant. Okay. So, now consider the previous equation N2 by N1, just substitute this formula here. N2 is e power minus E2 by kt and N1 is e power minus E1 by kt. Okay. So, this rearrange, finally you have e power minus h nu 21 by kT. Okay. So this rearrange this previous slide equation. So here n2 by n1 which is equal to e power minus h nu 21 by kT. Okay, so just rearrange e power minus h nu 21 by kT is nothing but this equation. Okay, since see nu 21 is exactly equal to nu 12 at equilibrium condition. Nu 21 is equal to nu 12 and likewise B12 which is equal to B21, and substitute in this equation and rearrange this equation. Finally, you have this equation nu 21 after rearranging everything. Finally, you have this equation nu 21 which is nothing but A21 by B21 into e power h nu 21 by kT minus 1. Okay. So, finally, it is A21 by B21 into e power h nu 21 by kT minus 1 whole power minus 1. Okay. So, the radiation density intensity according to Planck's radiation law. So, it's from black body radiation. Now, we are going to compare with this equation and black body radiation, Planck's radiation law. It is especially come from the Planck's black body radiation. So, after cancelling the common terms, the final term is A21 by B21 which is equal to 8 pi h nu 21 cube by c cube. So, this particular relation is called Einstein's relation. So, here A and B they are called as Einstein coefficients. Okay. Now, come to rate of spontaneous emission. We are going to find out the ratio. The rate of spontaneous emission to rate of stimulated emission, A21 by N2 by B21 into N2 by N2 nu 21. Okay. So, A21 by B21 into nu 21 is nothing but e power h nu by kT minus 1. So, this is the final equation. So, here there are two cases. One is if h nu is lesser than kT. So, this is the first case. If h nu, you know very well, E is equal to h nu, energy E is equal to h nu. Okay. So, if h nu is lesser than kT, so look at this term E h nu by e power h nu by kT. It is, suppose if you apply this condition or this case, in this condition h nu by kT is lesser than 1. So, what does it mean? This condition, the number of stimulated emission is more. Okay, this condition says when h nu is lesser than kT, what happened in this parenthesis? E power h nu by kT minus 1, it is nothing but h nu by kT is far lesser than 1. So, what happened ultimately? The number of stimulated emission, more or exceeds the number of spontaneous emission. Actually, it is happening in the microwave region. So, this is a condition in microwave region. On the contrary, when you come to the second case, if h nu is far greater than kT, delta E or E which is equal to h nu, this h nu is far greater than kT. So, what happened here? So, this one is more when compared to this one. So, h nu is greater than kT. The spontaneous emission is more predominant than the number of stimulated emissions. So, it is applicable or which is feasible in the case of UV visible region. I hope this lecture is very much useful to you. Thank you.